Hello again. So I'm here to give you a short discussion on binary search trees and how some of the function works. As you can see on the board, I have here and some comments pertaining to a definition of an array and some variable n and some variable size. So what uh, do I want to do with those values? So first, I want you to imagine an array of 10 elements and I want you to search a certain value, which is 25. So how are you going to do that? Actually, the answer is very simple. For any programmer can do it. Like for let's be more specific on Java, for example, for int I is initially set to 0, I is less than the max or the size, then I plus plus. Then inside here we can just check if ARR, if it's the array name, if ARR at I is equal to RR at I is equal to N, then that's it. You already have the condition. Yes, that is true. It's okay. Actually, it's good if you are just searching for a 10 element array. But the thing is, what if we are dealing with a bigger list? So, given a bigger list, like what if I ask you a million set of numbers? And maybe I'm looking for a value at around 700,005. So, how are you going to do that? So, it's a little unacceptable to use maybe a for loop. Imagine you're going to loop for, let's say, a million times just to look for a certain number. Maybe we're dealing with a number not really that um, equal to the current location. Like the number will start from 1, then comes 3, and then 7, then 4. And the range maybe, or not the range, the values can be any value of type long, then actually that will be some kind of problem. Yes, for beginner programmers, it's not that it's not something we put a lot of attention to. But knowing time complexity already, like what we did before, then you already know that there's something wrong with that. So given some certain condition, there are solutions which is way better than just using a for loop. Assuming the number is we are dealing with index list. Assuming we are dealing with sorted lists. Given those kinds of condition, that kind of condition, then we can do simple binary search, right? How does binary search work? It works by like we're just going to split the numbers. Like I'm going to copy this one. If I'm looking for 25 from this list and this is a sorted list, I just need to divide the list into two. Okay. So just by a simple condition, if it's greater than this value, the fifth element or the last element in the first half, then I can already check if it's on the upper bracket or in the lower bracket. So n is uh, greater than 13, then I don't need this list anymore. So all I need is this kind of list. Just by one simple if, we already cut the list into half. We can cut a million down to a 500,000 list just by a single if. That's how binary search works. And then maybe the condition uses div, and then considering whole numbers only, then this is the division. Then checking if it's 25, so we don't need this anymore because we're looking for 25, and then it will be cut into half again. And then there you go. It's not greater than, so it's there. Just by looking at or doing or performing 3 if execution, you already found the target. That's how binary tree works. So binary search tree is another kind of tree that is actually implementing that as one of the operations. So let me show you here the example tree that I prepared a while ago. So we have 15, okay, and then we have 8, 24, etc. Now, how does a binary search tree works, or are there rules for us to consider a binary tree to be a binary search tree? So actually the rule is very simple. It says that the value stored at the root of the subtree, if this is the current root we are looking at, and this is the subtree we are looking at, the value stored at the root is greater than any value in its left subtrees, any of the values in the left subtree here. So it's greater than any value in the left subtree. But it's less than, okay? It's less than any value in the right subtree. So that's the rule. That's how it works. So looking at this, number 8, if this is the current subtree, then any it's less than or it's greater than any value on the left subtree, but it's less than any value on the right subtree. Same is true with 24 and 19, 24 and 28 and 25. Okay, so that is a binary search tree. And if you're going to ask me, where can you find the smallest value or smallest element in the tree, then it's found in the leftmost element, this one. And the biggest or the largest value in the tree can be found in the rightmost element, which is this one. So that is a binary search tree. So looking at the operations, I'll be creating another video for the operations. But for now, maybe I'll start with a search algorithm. Let's create a simple search pseudocode. So looking at this one, let me just erase this and create a method. Let's name it search. I'll not be specific in any language, but I'll be more focused on the pseudocode itself. So search, for example, is a method that accepts two values or two parameters. One is the value you're looking for, and then the current uh, root or the root for the current subtree. Let's name it a root. So first, inside the tree, you might want to check if the root is null. If it's null, then most probably you just need to send a message like the tree is empty. Okay, tree is empty, and you also want to send a message that it's not found, and return simply return null. So it will go back. Okay. What if it's not null? So you check first the root or the data. Root the data again. I'll be using that. You might want to use other symbols that are highly specific on any language, but I'll just use root to activate the field for the pointer. field pointer. So root that data is equal to value. If the data inside the node is equal to the value we are looking for, then it's found. Send a message that it's found. Then return null. Return the root. Forgot to put this down a while ago. Okay. But what if it's not equal? Well, it's not found yet. We have two options. Either we traverse left. If it's not this equal to this one, if, for example, we're looking for 13, it's not equal to this one, then we traverse left or traverse right. So if the number, the value we're looking for is greater than, okay, then greater than this one, then we traverse right. If it's less than, we traverse left. Okay, or might as well just check the current value. If the current value is greater than the value you are looking for, then most probably you want to traverse left. But if it's less than the value you're looking for, maybe it's in the right part. So something like that. So let's look for the left traversal first. Let's go for the left traversal first. So if root that data is greater than the value, then all you need to do is search, call again. Take note, I'm doing a recursive call here. So search, but since we will be returning here, I might just want to end it. I can do return at the bottom here. I can return here, but it's much better to just return the method. Return search, but perform search first. Return, but perform search first using the value you're looking for, and then point the traversal to your left. So if this is the current node, then this is the left, this is the right. So left is pointing to this node's address, and right is pointing to this 24th node's address. So there you go. And then after that, you just check if root that data is less than the value. Then return search value then root that right. Go to your right. So there you go. That's the pseudocode. So you can easily convert this later on into a functional method in any specific language you want. But let's try to check. So if we are looking for the number 13, for example, then check first, is root equal to null? No. So is root that data equal to the value? The value is 13. So root that data is 15. No, it's not equal. So check if root that data is greater than the value. If root that data is greater than the value, which is 13, yes, then return search value root that left. So the value is still 13, then the address is root that left, which is actually this one being pointed by left. So this is the address. So when we go for another search call, search value, which is 13, and the root is the address of this node. So again, we'll perform the checking. Is it null? No. Is the data equal to the value? No. Is the data greater than the value? Is the data 8 greater than the value? No. So it will not perform this. It will be going to this one. Is root if root that data is less than the value, if root that data is less than the value, the 13 we're looking for, then you call search again, but this time pass the value and root that right. So root that, if this is the current root, this is root that right. So this will be the address being pointed by root that right. So now we have this. Once we call the search again, the new value, the value is still the same. The new root will be the address of this one. So checking if it's null, no. Is the data equal? No. Is the data root that data greater than the value? Is the root that data greater than 13? No. So it will go to this one. If root that data is less than, then again it will call the search value. But this time passing root that right. So root, this is the root that, this is the right. Root that right, right is pointing to the address of this node. This time, we'll call on search again and then passing the value and the new value for the root, which is this node. So is the root equal to null? No. Is root that data equal to the value? Is root that data equal to 13? Yes. So if it's equal to 13, then found, return root. So all the stock calls here will be uh, go we will be um, going back here, all the stock calls here, and then it will just return. Okay, it will just return until we're done with the stock is empty. Okay, so that's how a simple search algorithm works in binary search tree. Binary search tree. So maybe next time we can create, but we can create a functional code, but I think we need to finish all the operations first so we can create the actual code for all of them. And we have a running function, a running class wherein we can do searching, deleting elements in a binary search tree or inserting elements in a binary search tree. Okay, so that's binary search tree. So if you have any comments or question, please post it in the description in the comment section. So thank you very much for listening and have a good day.